We're in section 4.5 and we didn't quite make it through this example today. So where we left off was concavity and inflection points. Concavity has to do with testing the second derivative. So we had already found the first derivative in a prior part of the problem. So we picked up in the simplified version of the first derivative and found the second derivative. That involved the quotient rule. And then just like when we're checking intervals of increasing and decreasing, the sign in the first derivative for a prior part, it's kind of a similar thing here, but we're using the second derivative to see where it equals 0 or does not exist. So where we have division by 0 is where the second derivative does not exist, and that occurs at x equals positive or negative 2. Then we set the second derivative equal to 0, and what we figured out was that there was no solution to that equation. What that means in terms of the values we're trying to obtain here is that there isn't anything that we have to consider for when the second derivative equals 0. So kind of like the critical values for the second derivative, although we don't call them critical values, are just negative 2 and 2. So now we set up a similar table again as we do for our increasing decreasing test, but we're doing the concavity instead with the second derivative. So the intervals of x are going to be from negative infinity to our first value from the second derivative d/e or equals 0, so that was negative 2, then negative 2 to 2, and then 2 to infinity. Next, we're going to obtain a test x value so we can determine the sign of the second derivative. And that'll tell us the concavity on that interval. So the test x I'm going to use for the interval negative infinity to negative 2 is negative 3. From negative 2 to 2, I'm going to use 0. 2 to infinity, I'm going to use 3. And so for the sign, I'm not going to show all the work here, but I will for the first one. We're just plugging in negative 3 into the second derivative in its simplified form. And then we can play the sign game. If we do that, we get a negative on top over a positive in the denominator, which is a negative overall. And if you do a similar kind of thing for our other intervals and test values, you would get positive and then a negative. So when you have a negative second derivative, that means it's concave down on that interval. If it's positive, it's concave up. So as long as you have your information in a table like this, you don't have to restate the intervals of concavity. We do need to look at inflection points. We do have a change in concavity here. Having issues writing that down. Cavity at both x equals negative 2 and x equals 2. But remember our domain or other things we've encountered in this problem is that we don't have an x equals a point with an x equals negative 2 or 2 as a coordinate. It's not defined there. So a lot of different ways you could realize that we have a change in concavity here, but not the function's not defined here. And then we discovered with our limits we have some vertical asymptotes going on there. So that's what's going on. But anyway you do it, there's a lot of ways to slice this and dice this, but basically we don't have inflection points here because there's no point defined at negative 2 and 2. but we do have a change in inflection here. But since they're not points and inflection points, they have to be points, and we don't state them. So just annotate that a little bit here, so can't be inflection points. And we don't state. So now we finished that part, and the very last part left is the sketch. So I had some guidelines in section 4.3, and pretty much I just have an extension of that. First, plot important points. And we found quite a few of those. So we found some intercepts, which basically we found so that when we have the graph crossing the x and the y axis, we do it in the right place, because we're really trying to make an awesome graph. So those were some points that we need to plot. 9.5 is 4.5, so that'll make it a little bit easier. And then we also determined we have a local min at 0, 4.5, or 9/2. And then we had tons of asymptotes. The equations we had were x equals -2, x equals 2, and y equals 2. But as I mentioned when we went over that problem, part of the problem, we should also make sure we note the more detailed information, like x goes to -infinity, implied y goes to 2, so on and so forth. So I'm going to write them from left to right, because that's how I'm going to do my graph. So as x goes to -2 from the left, we figured out that y was going to -infinity. And then as x was going to -2 from the right, we found that y was going to infinity. As x is going to 2 from the left, y was going to infinity. As x is going to 2 from the right, y was going to -infinity. And finally, as x goes to infinity, y was going to 2. So we did a lot of limits in that section. So any symmetry, that might be a good thing. I'm using it as a check. I did everything as if, I didn't know the symmetry, just so I could kind of have, if something didn't jive, sometimes you make one mistake and then sometimes you can even make a graph that has those characteristics, and this would be something that if I noticed the symmetry was off, then I could know better where I made a mistake. So I like to do it that way. Do know how to graph with symmetry though. You will have some problems on your assignment where you're just given summary info and one of those could be symmetry and you're only given half the information. So you actually have to use the symmetry to graph. It's just a side note, I mentioned that in the beginning class too. Anyway, now I'm going to do my summary and plot points in that and actually start working on this graph. So I got to have the point 0, 4.5, -3, 0, -3, 0, and 3 to 0. So the x's go from -3 to 3, and then the y's are 0 and a little bit bigger than 0, 4.5. So kind of a good way to start my graph will be pretty much centered. Well, maybe a straight y-axis is in order, but maybe allow a little bit more space in positive y. I got to make sure that I at least have through positive and -3, but I do want to leave some space on the left and the right of those values so I can show the behavior after, before and after -3 and 3. For my y's, I have to at least go up to about 5 and then show some space above, have some negative x's included there because I have a y coordinate of 0, so a little space below that. So I'm in pretty good shape. I think I'll just go by ones here. 1, 2, 3, 4, 5. Should be pretty good. Now I plot my points. I have 0, 4, 5, 4.5, and then maybe I want to put some annotating things since I had just an intercept there, just a point on the graph. There's not necessarily anything going on special there at the moment. I don't write anything. Same thing for these other intercepts. Okay, now I get to the local min, and oh, 0, 4.5 is something special going on there. So local min. So maybe I'll just make some notes there. You don't have to, but that'll help me when I do the graph. Now we have some asymptotes, x equals -2, x equals 2, and y equals 2. So I might as well start sketching those in a little bit. I'm actually going to make my scale a little bit better, just mess that up a little bit. I could go ahead and put in some dotted lines. That's definitely going to help me make the graph. And y equals 2. Alright. And then I have all that limit stuff, which I'll use when I make the graph. It's got even symmetry and using that as a check, so the fact that those asymptotes are symmetric about the y-axis is definitely a good thing. Now I'm going to summarize my concavity, increase and decrease and stuff. So I'm just going to either reproduce my x-axis or make sure I'm keeping things to scale. And what I found is that the function is decreasing pretty much from negative infinity on. I did have something going on at -2 that, it didn't, there's a f prime does not exist, or is what was going on. So if I wanted to be a little bit more precise, I could write decreasing, just to know that it's not decreasing right at that moment at x equals -2. Similar kind of thing happened here, increasing from 0 to 2, increasing from 2 to 3. And then I'll extend this so that goes. Then I have my concavity, and I had a transition between -2 and 2. It was concave up, otherwise it was concave down. So putting that all together, I'll do that in the next recording. I might run out of time.